Dear students and viewers, in this video we are going to see how how a vector can be decomposed into three-dimensional coordinate system or the resolution of a vector in 3D. Okay. So, we are using GeoGebra classic version and the mode we are using, that is the GeoGebra 3D calculator. So, that is GeoGebra 3D calculator that you can see. Okay. Now, for this case, as you know, when we use a software or a CAD software, we have to define a vector in terms of its value. So, here we have taken a value. So, here you see that is actually due to the change. So, for that you can change it to some specific values, like say we can take here 5, then here 6. So, we are basically defining a point that is the end point of the vector that we want to resolve. So, resolution means basically resolving or decomposing the vector in its into its components. So, as if we are taking 5, 6, 7, that is the point of the, that is the coordinate of the tip of the vector. So, 5, 6, 7 is the coordinate of the tip of the vector, and in GeoGebra the tail of the vector is by default 0, 0, 0. So, but here we had option of defining the vector. So, after defining O and P, we have given a vector command to define the vector small p, that is from O to P. Now, as we do it, so it will be 5, 6, 7, that is from O to P. I thought you have understood that. You see, so here this is the vector, this one, and this is point O, that is the origin of the coordinate system, and this is the point P, that is the tip of the vector. You have three directions here. Red is denoting x direction, green is denoting y direction, and blue is denoting the z direction, as you can see. Okay. Now, you see that this is like this. So, initially we do not have the components, we have simply the vector, and finally we will we want to resolve this black one in terms of it, or this one, that purple color vector, into its components in the x direction, that is the red one, in the y component, that is the green one, and in the z direction, that is the blue one. Okay. Now, and how the components and the vector itself are connected or related, we will show in terms of geometry. Okay. So, what we have done, I will just discuss that. Now, what is the meaning of a vector component? Vector component means basically in 3 dimension, if I want to get the component, I will basically drop a perpendicular from this tip of the vector to all the 3 individual directions, and where they will intersect from the origin up to that point of intersection, that will be the length of the component, and direction is obviously along the coordinate direction. That is if it is from this to this, then it is x direction, that means x component. If it is on the y coordinate system, it is the y component, and if it is from this up to the z axis, it is the z component. Okay. So, we can show it. So, from this we can show perpendicular line So, perpendicular line we can show. So, if it is from x on this, it is this, from this point on this, it is this, and from this, now I say select here, but it will pass through this point, you can clearly see. Okay, even if I select here, it will pass through that point because that is the component. So, you can again verify. Okay. So, you see that how we have got it. Basically from this point I will draw perpendicular lines. So, these are, that means red, green and blue, these are three mutually perpendicular directions. That is the definition of a set of orthogonal coordinates. Orthogonal means perpendicular to each other, as you know. Perpendicular means 90 degree with respect to each other in the 3D space. So, now this is the vector, it is oriented in any general direction. Now, from point P I will just draw perpendicular on the x line, and you see that it will pass through this point, the tip of the vector. So, anywhere I select, even if I select this direction, it will pass through this point. That will give you the idea that this is the length of the component. So, you see that that is passing through this point. Even if I say next, I will select again this point and I will select anywhere on this line. So, there will be only one perpendicular from a point on a line. So, definitely that it will pass to this point. Okay. Next, you see that I select again this point and I select anywhere on this z direction. It may be here, it may be here, anywhere, but in this software it will show that it will pass to this point. That will give you the idea that this is the perpendicular, that is the only perpendicular, and there should not be any ambiguity. Okay, you see. Okay. Now, just let me reorient it, rotate it, so that you can visualize more clearly. You see that from this point I can draw three perpendiculars along the three different directions, and wherever they will intersect, that will be the component along that particular direction. Okay. So, first of all, that should be clear. So, from the point of view of dot product, as you know that if I want to get a component of any vector, say for example any vector, this vector, say this one, any vector, this one, if I want to get a component. So, let me enlarge the thickness of the actual vector so that you can clearly see the original vector and its component, or separate the original vector and its components. So, this purple color vector is the original vector and the other three are the components. So, vectorially the red vector, green vector and the blue vector, if we add them, they will basically give you the, as a resultant, this vector. So, this is the vectorial sum of these three. Okay. So, that should be clearly kept in mind. So, that means when you will draw, you will draw with that sense that one vector is decomposed into 3, so that vectorially they will add to give you this 1, or 1 is decomposed into 3. Okay, either these 3 are existing or this 1 is existing. So, at a time only either this is there or these 3 are there. So, that should be kept in mind. Okay. So, that means what? That means when one vector is decomposed, the original vector will not remain. So, that will be divided into 3 vectors. So, that vector cannot remain at the same time with the component. So, either the components are there or the vector itself is there. That means while drawing that, you have to depict it like that. Okay. Or if you show the components, you will not show the vector, original vector in the same color or thickness like that. So, that should be separating the original vector and the that means your way of drawing or way of representation should clearly indicate that either these 3 are there or this one is there. Okay. because most of the students I have seen that they draw with the same line type or the same pen color, and it becomes difficult to understand that whether there are one vector or four vectors. 4 means along with the resultant, if you draw the along with the resultant vector, if you draw the components, that will basically show 4 vectors. So there are only 3 vectors as decomposed vectors, or there is only the resultant or the original vector. So that should be kept in mind, because that is a very conceptual part. I am repeating it again and again, that should be clearly understood. Okay. Next, another thing is, as I told in the class, you see that in some other way, how can I basically draw the vectors? Basically you see that other ways of doing that, that means from this point I can draw perpendicular on the plane also. That means these are the 3 mutually perpendicular planes, as you can see, one is this plane, another is this plane, another is this plane. So say for example, the plane which is perpendicular to the x direction, that is called the x plane. So red is in this direction, so here this plane is called the x plane, as it is perpendicular to the x direction. Okay, you see that which one is x plane, therefore this is the x plane, this one. Okay, let me select that. Yes, this one. So red line is perpendicular to this plane, therefore this is called x plane. Actually x plane means yz plane, because y and z both are perpendicular to x direction, therefore yz plane is definitely perpendicular to x direction, that is also called x plane. Yz plane is also called x plane in different type of nomenclature. Okay. And what is the y direction? Green. Okay. Next, therefore what is the y plane? This plane is y plane, right? This is perpendicular to the y direction, that is called y plane. Y plane means what? Perpendicular to the y direction, this plane everywhere the y value is constant. So for this particular selected plane, the value of y is 0 everywhere, you can understand. So it is the reference for the y direction, so it is 0 everywhere, and for this plane everywhere the x value is 0. So that is why it is called x plane. So constant x value everywhere. So as you have seen equipotential surface, right? So that is everywhere the potential energy is constant, like that. So that is why it is called x plane, that is everywhere the x value is constant, on this plane everywhere the y value is constant, and on this plane, this third one, say this one, and on this plane you see somehow it is, yes, this one, the gray color line, this is the plane which is called the z plane, sorry, this one is called the z plane, this gray color plane is called the z plane. Okay. So these are the 3 planes. Now we will draw perpendicular also. So these perpendicular lines we will remove and we will show the, now these are the perpendicular on the axis, first these 3, these are the perpendicular on the axis, this one and this one, these are the perpendicular on the axis. Okay, so these 3, these are the perpendicular on the axis, and we will show now perpendicular on the planes. So how to get the components? So that was a question, right? So now we will draw perpendicular from these on the plane. So let us draw that. Okay. So, you see that this is from P on the it is on the z plane. Next you see from P on the y plane, this is the y plane. So, it is from P on the y plane and this is from P on the x plane. Now, we have drawn perpendicular from the vector tip to the planes. Okay. Now, they are intersecting. So, we can determine the point of intersection with the line and the plane. So, individually we can determine. So, let us see that. You see, so this is the point of intersection, this is the point of intersection of the line and the plane. Next you see this is the point of intersection of the line and the plane, and another, this is the point of intersection of the line and the plane. Okay. Next let us see. Now, we have connected this point and this point. You see that therefore, directly from this point if I drop a perpendicular, that means once I drop a perpendicular from the tip of the vector, that means from this point on this plane, then I drop a perpendicular from this point on this plane and therefore, it intersects here, therefore, this is the component. Okay. Next we see we have again drop a perpendicular from this point on this plane and that intersects this line here. So, that is the component. So, that is the x plane. So, perpendicular to the x plane we have dropped a perpendicular and this is the y, that means it is xy plane. So, it is x component along the x direction, it is y component along the y direction. Next we drop a perpendicular here, that means we have just connected this point to C to show that they are basically, that means from this point we have dropped a perpendicular here, again from this point we have just dropped a perpendicular on this plane and we have seen that they are intersecting here. So, that is the z component. Okay. So, what I said, from this point, that is from P on the x plane, whatever perpendicular I have dropped, from this point again I have dropped a perpendicular on x and that is the point where it intersects the z direction, that is the z component. Okay. Again we have confirmed that. So, from this point we had dropped a perpendicular on the y plane and from this point again we have dropped a perpendicular on the x plane and they are intersecting here. So, that confirms. Okay. Again you see that again from this point we are dropping a perpendicular here and again it is confirming that. So, that will basically produce the rectangular parallelepiped by this wire frame, right. Again we are confirming it from this point if we get, and then that point will be confirmed. So, they will basically give you the same point of intersection. Okay. Now, these are the things that we had already seen. So, now see that the rectangular parallelepiped that I was discussing. So, that is the, this is this. So, this is the thing, okay, here, that is this. So, we can drop here and all are there ready, yes, drop here. Now, if we just show it with some line segment command, you can So, see, let us see. Now we can remove the earlier lines, perpendicular lines, to show that the first perpendicular we will drop this one, and we will determine the point of intersection, that is A, B and C. So, C we have to keep A, B, C. Okay. Next we will just drop that, we will connect that. So, it is this to this, then this again to this, this to this, this to this. Okay. So, that is the basically rectangular parallelepiped formed by these 12 lines. So, here 4 on this surface, 4 on the back surface, and the edges, 4 edges. So, they are basically the 12 sides. Out of them 3 are basically the components, and they are having multiple things. So, for example, all these are basically equivalent to, so basically how many sides are there for this rectangular parallelepiped? 12, and these 4 are same. As you can see, these 4 are basically all are equivalent, that is equal to the x component value, and all these sides, so 1, 2, 3 and 4, all these are equal to the y component, and this one 1, 2, 3 and 4, they are basically equal to the z component. So, I guess you have understood this. Okay. So, thank you for watching.